So, good morning, friends. In the third lecture, we have discussed the uniqueness theorem, static method of analysis of beam, kinematical method of analysis of beam, and some examples. So, in the previous lecture, we have discussed how to find the shape factor as well as plastic moment for the different continuous beam as well as simple beam using the static method and the kinematic method. Now, what is the uniqueness theorem? If a bending moment distribution can be obtained which satisfies the three conditions of mechanism, equilibrium and yield, then collapse load corresponding to such bending moment distribution will be the true collapse load. Mechanism condition means sufficient number of plastic hinges developed to transfer the structure into mechanism. It is also called as kinematical condition. Equilibrium condition means bending moment distribution is in equilibrium with the collapse load. It is called as the static condition. And third is the yield condition. Yield condition means bending moment does not exceed the plastic moment, that is EMP. Now this is the concept of the uniqueness theorem. Here it is observed that this line indicates the maximum value of the moment, that is the plastic moment, and this is related with the true collapse load, or we can say that W is equal to actual load is equal to the collapse load or ultimate load. And that's why at this point all three conditions are satisfied. Here W is equal to W. Kinematic theorem, we can say that the W is greater than or equal to W, and for the static theorem W is less than or equal to W. At this point all three conditions are satisfied. That's why it is called as the uniqueness theorem, and this is related with the static theorem and this is related with the kinematic theorem. That means W is greater than or equal to W. In static theorem W is less than or equal to W. Now this is the lower bound theorem. It is also called as the static method or static theorem. If the bending moment distribution can be found which satisfy the condition of equilibrium, this is the first condition, equilibrium, and second is the yield. Then if both conditions satisfied, then the corresponding load is less than or equal to the true collapse load, and that's why equilibrium and yield condition are satisfied but not mechanism condition. That is W is less than or equal to W. It is also called as the static method. This theorem is used to analyze the simple cases of the beam. It is also called as the shape theorem. This is called as the shape theorem. Second theorem is called as the upper bound theorem. If the load obtained from any assumed mechanism, here we have considered the mechanism, for a given structure greater than or equal to the true collapse load. In this case, mechanism and equilibrium condition are satisfied but not satisfied the yield condition. That is W is greater than or equal to W. It is also called as the kinematical theorem or method. This theorem is used to analyze any type of beam, that means the continuous beam as well as frame. It is also called as the unsafe theorem. It is called as the unsafe theorem, and lower bound theorem is called as the safe theorem. Now the design steps. Analysis of beam for the collapse load by static method or lower bound theorem. Few steps are similar used in the lower bound theorem as well as in upper bound theorem or static method or kinematical method. First step, to find out the static degree of the redundancy, DSI is equal to R minus E. What is R? R is the number of reaction component and E is the number of equilibrium equation available. Then find the number of plastic hinges developed in the beam. That is equal to DSI, degree of static indeterminacy, plus 1, that gives the number of plastic hinges developed. Similarly, find out the support reaction, then we can find out the support reaction and draw the bending moment diagram. Then compare the plastic moment with the elastic moment and find out the collapse load. This is the steps used in the static method. Now in the kinematic method, first this step is again same, find out the degree of redundancy, that is the DSI is equal to R minus E. Number of plastic hinges required for the collapse mechanism, N is equal to DSI plus 1. Then find number of possible mechanism found. Number of, that is equal to number of plastic hinges developed minus DSI. Now this is the number of plastic hinges developed minus DSI, and then we can find out the collapse mechanism. Using the principle of virtual work, find the collapse load for the each mechanism. and safe collapse load will be the lowest of the load found in all the mechanism. This is the second method. Now we have discussed one by one. In case of static method, this is the simply supported beam subjected to say point load W, and here I have written W is equal to WC, that is the collapse load, and it is acting at a distance of L by 2, total span is L, and that's why the bending moment diagram is 0 at the support, and maximum that is equal to W or WC into L divided by 4. Maximum bending moment, it is triangular because there is a unit load, point load. So as per the assumption in theory of plasticity, we can say that the bending moment is maximum at the center, or we can say that below the load there is a chances of the failure of the section. That means the plastic hinge develop at the below the load, and therefore we can say that this elastic moment is equal to plastic moment. Therefore MP is equal to WC L by 4. MP is equal to ME, that is MP is equal to WC into L by 4, and that's why WC is equal to 4 will be 4 multiplied by MP divided by L. That gives the collapse load. That is the static method. Now these are the some tips to analyze the structure using the kinematical method. Prediction of the plastic hinges. Generally at fixed support plastic hinges are developed. Second, at the rigid joint in case of the frame, rigid joints are there, and at that point there is a chances of the plastic hinges. At interior support, that means if the support is continuous, number of supports are there, as in case of continuous beam interior support, there is a development of the plastic hinges. At point load or concentrated load, there is a development of the plastic hinges. Now plastic hinges are not developed at roller support or simple support or hinge support and the free support. If static redundancy DSI is equal to number of hinges developed, that is N, then it makes the structure determinate. Now this is the second method, that is the kinematical method or upper bound theorem, in which we have considered there is a chances of load is here. This is the simple support, here both are simple support, that's why there is no chance to develop the plastic hinge, but below the load there is a chance to develop the plastic hinge, and that's why because of this load this is the maximum deflection, and at this point there is a development of plastic moment MP. This is let we have considered this is theta, as it is symmetrical, that's why this is also theta, and this is the delta. Now tan phi, this is the phi or theta, and this phi, tan phi is equal to phi because this angle is very small. Therefore phi is equal to delta opposite side divided by adjacent, delta divided by this distance is L by 2, delta divided by L by 2, that is equal to phi. Then apply the principle of virtual work, in which external work done by this force W, that is equal to the internal work done. Now internal work done is related with the moment multiplied by its rotation. Now at this point there is no chances of development of plastic moment, that's why MP is 0 at this and this point, and here it is MP multiplied by this total angle, this is the exterior angle, and this angle is equal to, we can see that if you draw the line like this, these are the two parallel side and this is the intersected line, and that's why this is theta. Similarly if you extend this, here it is observed that this angle and this angle is theta, and that's why this is theta, this is also theta, and we get the total angle is 2 theta. So external work done is equal to WC multiplied by delta, force multiplied by distance, WC multiplied by delta is equal to internal work done, that is MP. Here MP is 0, that's why MP multiplied by 0 multiplied by phi, it is 0, that's why it is MP multiplied by 2 pi. MP multiplied by 2 phi is equal to WC into delta. From this we have this relation, phi is equal to delta into L by 2, or we can say that delta is equal to L by 2 multiplied by theta. So WC, delta is eliminated by phi into L by 2, that is equal to 2 MP multiplied by phi. This phi will be cancelled and we get the WC is equal to 4 MP divided by L. This is the kinematical method. Now second problem, here we have considered the different cases. Here 2 point loads are there, 1 point load at the different distance A and B, and A and B is equal to L, cantilever, and the UDL, simply supported beam subjected to UDL. Now first we have considered the simply supported beam subjected to UDL. In this case we have considered that whatever the load acting on this is W kilonewton per meter, and that's why here W multiplied by L is equal to WC, that is the concentrated load. Here this value, maximum bending moment in case of the simply supported beam subjected to UDL, it is WL square divided by 8, and W into L, that is equal to WC. So WC into L divided by 8 is the maximum bending moment. And MP, again we have considered, if you consider the resultant force which is acting at the center, and that's why plastic hinge develop at the center. These are the two simple supports, that's why no plastic hinge, therefore 0 MP, and MP is there. Again this is phi, this is phi, as it is symmetrical, therefore WL is equal to WC, collapse load. So WC multiplied by this delta, here UDL is there, that's why we have considered delta by 2, and is equal to external load is equal to internal load MP multiplied by 2 times of phi. Now in this case we have consider the both method, comparison of both method. Plastic hinges develop at the center of beam, therefore equate MP is equal to ME, that's why MP is equal to WL into L by 8, WL square by 8, therefore W into L is equal to WC into L divided by 8, therefore WC is equal to 8 MP divided by L. This is the static method. For simple cases, standard cases, it is very simple. Then in kinematic method, we have considered the principle of virtual work. We use this diagram. For this diagram, WL is equal to WC, that is WC multiplied by, here the UDL is there, uniformly distributed load is there, that's why this distance is equal to delta by 2. That's why external work done is equal to WL, which is denoted by WC, into delta divided by 2. Because there is a UDL, is equal to external work, then internal work is equal to MP multiplied by 2 times of phi, MP multiplied by this total rotation. And again tan phi is equal to phi, repeat the same procedure, tan phi, phi is very small, is equal to phi is equal to delta divided by L by 2. So delta is equal to phi L by 2 and WL is equal to WC, therefore W into L is equal to WC and delta divided by 2, that is 1 by 2 into, eliminate this, delta is equal to theta L by 2, that's why phi L by 2, phi L divided by 2 is equal to 2 MP multiplied by phi. This phi will be cancelled and we get WC 8 is equal to 8 MP divided by L, similar to the static method. One more problem we have discussed. Again this is the standard case. There is a cantilever subjected to point load. Now this is the bending moment diagram. Cantilever beam, maximum bending moment at the fixed support, and due to this load WC multiplied by L is the load. This is the diagram, bending moment diagram. And in kinematic method we have considered, due to application of load, there is a chances of the plastic hinge develop at this point and this point. And so we have apply the load, what happens, there is a deformation delta, and that's why this is the deflected form. At this point, because of the fixity, there is a chance of plastic moment is there, plastic moment multiplied by theta, this is the external work done, and WC multiplied by delta is the internal work done. So kinematic method, internal work done is equal to WC, that is the collapse load, multiplied by delta, WC into delta is equal to internal work done due to the moment. So MP, because of the fixity, at fixed support there is a chances of the plastic moment, that's why MP multiplied by theta. So MP multiplied by theta is equal to WC into theta by L, because delta is equal to, again this delta, tan theta is equal to delta divided by L. So delta is equal to theta into L. So WC theta L is equal to MP into theta. So we get the collapse load is equal to MP divided by L. In static method, we have equate the MP plastic moment development at the critical section, plastic hinge, and that's why WC into L is equal to MP. WC into L is equal to MP. This is the elastic moment, this is the plastic moment, and from this we get the WC is equal to MP divided by L. This is the static method, this is the kinematic method. These are the determinate beam, and that's why no need to use the to find out the DSI, degree of static indeterminacy. Now fourth problem, this is also related with the point load, simply supported beam subjected to point load at a distance of A, and that's why the bending moment is equal to WAB divided by L. This is the standard case, and again as per the assumption we can say that below the load there is a chances of development of plastic moment or plastic hinge, and that's why this MP is equal to WAB divided by L in case of static method, and we get the value of W, and this W is eliminated by WC. In kinematic method, repeat the same procedure. Below the load there is a development of the plastic hinge, and that's why this is the simple support, that's why this MP is equal to 0. Here also MP is equal to 0 because these are the simple support. Plastic hinge developed below the load, that's why this is MP. And again repeat the same procedure, this MP multiplied by total rotation, it is theta, and here angle is different because the distance is different, A and B. So this is phi, this is theta, therefore this total angle is equal to theta plus phi. So we can say that the internal work done is equal to external work done using the principle of virtual work. WC multiplied by delta is equal to MP multiplied by, here it is 0, MP multiplied by theta plus phi. And then we can find out the delta. Tan theta is equal to delta divided by A. Similarly, tan phi is equal to delta divided by B. This is the static method. We get the WC, and this is the kinematic method. Tan theta is equal to theta, that is equal to delta by A because theta is very small. Therefore, similarly, tan phi is equal to phi, that is equal to delta by B, and theta is equal to delta by A. So eliminate this and we get the W into delta, MP into theta is equal to delta by A, and phi is equal to delta by B. So this delta will be eliminated. WC is equal to MP into A plus B is equal to total length L and divided by AB. We get the WC is equal to MP L divided by A by B, which is similar to the static method. This is the static method, this is the kinematic method. Similarly, if we consider the cantilever beam subjected to UDL, the bending moment diagram is parabolic, and we know that this WL into L by 2, and WL again here WL square divided by 2 is equal to WL into L divided by 2, and WL is equal to WC, and that's why WC into L by 2 is the maximum bending moment in case of static. This is the elastic moment, and that's why here again there is a UDL, therefore plastic hinge always develop at the fixed support. So we can say that WC into L by 2 is equal to MP. Here MP is equal to WC into L by 2, and that's why we get the WC is equal to 2 MP divided by L. In kinematic method, equate the external work done is equal to internal work done, that is the principle of virtual work, and we can say that this is the delta, this is the theta because it will bend like this, this is delta theta, and here due to fixity there is a plastic moment MP, and so we can say that internal work done is equal to MP multiplied by theta because this is fixed, and external work done is equal to WC. WC means it is W into L. So WC into, because of the UDL we have considered this distance is delta by 2. So WC into delta by 2 is equal to MP into theta. Again we can replace tan theta is equal to theta is equal to delta by L, total distance. Therefore delta is equal to theta L. So WC into theta into L by 2 is equal to MP into theta. Again we get the same value, 2 MP divided by L, similar to the static method. Now we have considered the continuous beam. In this case we can find out the value of MP, that is the plastic moment. What is the shape plastic moment? This is the example. Here the span is given 4 meter, 3 meter, 1 meter, again 4 meter, and 2 meter, 2 meter, again 4 meter. This is say support A, support B, support C, support D. Now AB subjected to the UTL, BC subjected to the point load at A distance and B distance, and load is 2 times of WC, and for the second it is 4 times of WC, point load at the center. Now first of all we have considered only this portion, that means the first beam AB. Here again it is observed that there is a development of the plastic hinge at this point, and that's why we can say that there is a development of MP at this point due to the load. Below the load it is MP, and at this point this is the continuous support, and that's why at continuous support again moment is there, that is MP. So external work done is equal to WC multiplied by delta is equal to internal work done is equal to MP multiplied by theta plus MP multiplied by 2 theta plus MP multiplied by theta. We get the value of MP. Okay, similarly this is the first diagram. For second diagram again we have considered this is fixed, continue, because of the continuity there is a moment, say MP. This is also continue, that's why again there is a moment, plastic moment, development of the plastic hinge at this point, and below the load, and that's why this is also MP. So when we analyze using the kinematic method, we can say that 2 times of WC multiplied by delta is equal to MP into theta plus MP into theta plus phi plus MP into this is phi. Okay, similarly third one, in third case this is fixed, again this is fixed and this is continue, that's why there is a development of plastic moment at C support, plastic moment at D support MP, and the plastic moment below the load. So when we use the kinematic method we can say that 4 times of WC multiplied by delta, force multiplied by distance, is equal to displacement is equal to MP into theta, that is the internal work done at C support, internal work done due to this load, that is MP multiplied by 2 theta because it is symmetrical, and MP multiplied by theta at support D because it is fixed. But sometime when in the problem if it is not fixed, we have considered this portion is hinge or roller, in that case this MP is equal to 0. Remember, rest of the procedure is same. Now first step, this is the continuous beam which is indeterminate, and that's why we have used the following steps. In the previous examples we have skipped all these things because these are the static. This is now indeterminate, that is the externally indeterminate. First of all we can find out the degree of static indeterminacy is equal to R minus E. What is R? R is the number of unknowns. Here 2 unknowns are there because in case of beam we have neglected the horizontal deformation or axial force, and that's why due to the transverse load we have considered, or we can apply only 2 equations, that is summation Fy is equal to 0 and moment about any point is equal to 0. So R is equal to, here there are 2 unknown, that means the 2 reaction, one is the vertical reaction and second is the moment, and third reaction we have neglect is because of the neglect of the axial force. 2 here, 1 is there, roller support 1 is there, and again 2 plus 1 plus 1 plus 2, 2 1 3 4 5 6, that's why R is equal to 6, and number of equations available when we apply for the continuous beam A B C D, we can say that only 2 equations, that's why 6 minus 2, 4 is the degree of static indeterminacy. Then step number 2, to find out the number of plastic hinges required for the collapse mechanism, that is N is equal to DSI plus 1. DSI is equal to 4 and plus 1, so 5 number of plastic hinges requirement is 5. Now number of possible mechanism found, that is the number of plastic hinges developed minus DSI. Now the number of plastic hinges developed, 1 hinge developed due to the fixity, 1 hinge developed due to the continuity of the support, 1 is developed due to the continuity of support, and 1 is developed due to the fixity, that means 1 2 3 4. Then due to the load at the center there is a development of plastic hinge, 1 2 3 4, then 5 1 6 1 below the load, and 7 1 again below the load. That's why number of plastic hinges developed is 7. DSI is equal to 4, say 7 minus 4, we get the 3. That means the three mechanisms are required to analyze this beam. So first mechanism, second mechanism, and the third mechanism, it is sufficient. So this is the first mechanism. Here we have considered the load WL is equal to WC because there is a UDL, and internal work is equal to WL is equal to WC into delta by 2 because of the UDL. So WC into delta by 2, it is the external work done, is equal to internal work done. Due to fixity, there is a moment at support A, that is MP, moment below the load MP multiplied by 2 theta, and then due to continuity again there is a MP same direction multiplied by theta. So MP into theta plus MP into 2 theta plus MP into theta. Again we can say that tan theta is equal to delta by 2, therefore theta is equal to delta divided by L by 2. So we get that WC is equal to 16 MP divided by L. Here L is equal to 4 meter, so it is 4 times of MP. That is the mechanism number 1. Now we have considered the second mechanism, that means we have considered the second beam. Here this is the support B, support C. In this case, because of the continuity, there is a moment, say MP. Below the load there is a development of plastic hinge, that is MP, and because again continuity, there is a plastic moment MP in the same direction. So MP into theta plus MP into theta plus phi, because the load is at the different, it is not at the center. So this is theta, this is phi. That's why this total angle, exterior angle, is equal to theta plus phi. So external work done is equal to 2 WC multiplied by delta. This is 2 WC, it is already given in the example. 2 WC multiplied by delta, this distance, is equal to MP multiplied by theta plus MP multiplied by theta plus phi plus MP multiplied by phi. So 2 MP theta plus 2 MP phi. Again tan theta is equal to theta, that is equal to delta by 3, and tan phi is equal to delta by 1. So we get the value of theta and phi in terms of delta. So 2 WC into delta is equal to 2 MP into theta is equal to delta by 3 and phi is equal to delta. So we get the WC is equal to 1.33 MP. This is the equation number. This is the equation number 2. Previously it is equation number 1. This is equation number 2. That is second case. And then third mechanism. We use the third mechanism for this point load at the center. Say 4 WC load already given. 4 WC multiplied by delta. 4 WC multiplied by delta is equal to continuity. There is a plastic moment MP. Below the load, plastic moment MP is there. MP multiplied by 2 theta. And again, because of the fixity, again there is a moment, plastic moment MP. So MP multiplied by theta plus MP multiplied by 2 theta plus MP multiplied by theta. This is related with the internal work done. And 4 WC multiplied by delta, that is related with the external work done. External work done is equal to internal work done. We get again theta is equal to delta divided by 2. It is symmetrical. So eliminate the delta and we get the WC is equal to 0.5 MP. This is the case number 3. So from the case number 1, 2, 3, safe load or true collapse load on the beam, WC is equal to, that is the lowest. We can take the lowest. First answer is 4 MP. First answer is 4 MP. First mechanism. Using the second mechanism, second answer is 1.33 MP and third answer is only 0.5 MP. So safe load is 0.5 MP. In many times in the example, the value of MP is given. When we multiply it with, that gives the safe load in kilonewton. This is the example. And this may be asked for the 7 marks. Now, this is related with the beam. Now, when we consider the collapse mechanism as in case of frame. Frame is a combination of vertical and horizontal member, that is the column and beam. There are different possible collapse mechanism. For the analysis of frame, by kinematical method, mainly 3 mechanisms are considered. Actually there are 7 mechanisms, but we have considered 3. First is the beam mechanism, in which we can say that at the rigid joint 2 plastic hinges are developed, and below the load 1 plastic hinges is developed. So necessary 2 rigid joint and 1 at the load point. This is the 3 plastic moment. Second, sway mechanism. That means the column, because of the load, column may be sway like this. It will be rotate from this to this, and this is called as the column mechanism or sway mechanism, in which at the joint, that means we have considered if this is fixed, this is the frame, and because of the load this frame will be transferred here. That's why plastic moment develop here at this point and at this point. Four minimum mechanisms, 4 mechanisms are developed. Third one, we have considered the combination of the beam mechanism as well as the column mechanism. This is the 3 cases. Now for example, we have considered this is the beam, say frame A, B, C, D. In case of kinematic method, we have considered this is fixed, and these are the 2 joints. Rigid joint, that's why this is fixed, that's why there is a development of the plastic hinge at this point, plastic hinge at this point, plastic hinge below the load, and plastic hinge below the load at this point. Okay, so we have considered the beam mechanism. Beam mechanism is related with the bending. So we have considered this BC, 2 times of WC load is there. Because of this there is a development of this is the delta is the deflection. At point C we have considered, because of the rigid joint there is a moment, that is the plastic moment. This is also plastic moment below the load, and at this point this is also joint, rigid joint, that's why plastic moment MP. Second, again beam mechanism, because of the load. If load is provided at this point, then this will be not raised, but if load is provided in between the 2 ends of the column, in that case it will be bent, and that's why we have considered beam mechanism. Again repeat the same procedure. We have considered this is the fix, that's why moment is developed at the joint A, that is the MP. Because of this force load there is a delta, and that's why here below the load there is a development of MP, and this point again this is the rigid joint, and that's why this is the moment MP. This is the beam mechanism. Similarly, sway mechanism. For sway mechanism means if this is the frame, this frame will be shifted here because of the load, and this frame is also shifted this point, and that's why if this is theta, this is also theta, alternate angles, and if this is displaced with delta, same will be displaced from the other column. This is also delta, that's why this is theta, this is theta. Now again using the kinematic condition, we can see that this is MP multiplied by theta. Again MP multiplied by theta. Here also we can say that MP multiplied by theta, and again this is also MP multiplied by theta. So MP multiplied by theta plus MP multiplied by theta plus MP multiplied by theta plus MP multiplied by theta, that gives the total internal work done, and external work done is related with WC multiplied by this distance. We know that delta, this distance is known. From similarity of triangle we can find out this value. Okay, and third case is the combined mechanism, that is the beam and column. That means beam will be bent like this, column will be bent like this. That's why this column initially vertical, because of this load it will shifted like this. This is theta, this is theta, this is theta, this is theta, and because of this load it will be shifted in this way. Again this is theta, and this angle is 90 degree. This is the assumption. If this angle is 90 degree, this angle is 90 degree, that's why this is theta, this is also theta, this is also theta. If this is delta, and depending on the distance we can see that this is also delta or delta dash. This is the third mechanism. Now we have considered the problem. In this problem, find out the plastic moment. Load is given W 25 kilonewton, here 50 kilonewton, but this load acting at the joint. So first beam mechanism, we have considered this diagram, that is this point, say this is A, this is B, this is C and D. At point B there is a theta, and the plastic moment, because of the rigid joint, plastic moment will be developed, MP. And due to the load, again there is a plastic moment, MP, and this is theta. Load is not at the center, and that's why this is theta, this is phi, this is delta. So again this is also joint, rigid joint, and that's why this is also MP. Okay, so we have discussed one by one. A rectangular frame whose legs are fixed at the base and carries 2-point load, one on the beam and second at the column beam joint as shown in figure. This is the problem. Find the plastic moment if cross section of the frame member is same. Cross section is same, area of the section is same. Now step number 1, dsi is equal to r minus e. R is the number of reactions and e is the equations available. Now in this case, this is the combination of column and beam, and that's why here 3 unknowns are there. One is vertical reaction, second is horizontal, and third is the moment. This is 3, this is 3. That's why 3 plus 3, 6 unknowns are there. R is equal to 6 and equation available, equilibrium equation is 3. So 6 minus 3, 3 is the degree of static indeterminacy. Then find the number of plastic hinges required for the collapse mechanism. N is equal to dsi plus 1. That's why 3 plus 1 is equal to 4. Then find the number of possible mechanism found. Number of plastic hinges developed minus dsi. Number of plastic hinges developed. In this case, we have considered at this point because of the fixity, at point D fixity, at the joint, rigid joint 1, 2, 3, 4, and below the load, because here there is no chances because the load exactly at the center. Okay, that's why 1, 2, 3, 4, and 5. 5 are the possibility of the plastic hinges developed, NPH, and 3 is the degree of static indeterminacy. 5 minus 3, that means the minimum 2 mechanisms are required. Okay. Now first of all, we have considered the beam mechanism, in which we have considered this beam A to B to C subjected to 50 kilonewton load, and that's why this is theta, this is delta, and this is phi, as we have discussed. And therefore external work done using the principle of virtual work is equal to internal work done. So 50 kilonewton is the load multiplied by delta is equal to here MP multiplied by theta, because rigid joint, plus here also because of the load there is a development of plastic hinge MP, again multiplied by theta plus phi, plus again this is the rigid joint, and that's why this is also MP multiplied by phi. So again tan theta is equal to delta divided by 1 is equal to tan phi is equal to, we can see that delta divided by 3. So after modifying or convert the delta in terms of theta and phi, we get the value of MP. Here MP is equal to 18.92 kilonewton meter. This is the case number 1, that is the beam mechanism. Second, we have considered the sway mechanism, in which we have considered because of this load the frame will be shifted here, made by delta. This is also delta, and this angle is same. Due to fixity, there is a plastic moment, and this will be shifted here because of this load, and that's why again plastic moment is developed at this point. At this point also we can say that there is a development of the plastic hinge MP in the same direction, and here also it is MP. So MP multiplied theta, MP multiplied theta, MP multiplied theta, MP multiplied theta. These are the 4 times of MP multiplied by here. Sorry, theta is there. This is also theta. This is not phi because this is same, and 25 into delta is equal to MP multiplied by 4 theta. So this will be eliminate, and we get the MP is equal to 25 kilonewton meter. This is the case number 2, that is sway mechanism. And third mechanism, that is called as the combined mechanism. That means the column will be shifted here. This distance is delta. Here we have considered because of the load on the beam, it will be deflected like this, and this angle is 90 degree. So we have considered theta multiplied by MP. Again this is theta multiplied by MP. At this point, due to load, this load, we can say that this is the MP multiplied by this is theta. Load is at the not at the center, theta plus phi. Okay, so So 50 into delta, we have considered this is delta say, plus 25 multiplied by this distance, that is delta, is equal to mp multiplied by theta, mp multiplied by theta plus 2 mp multiplied by, this is theta, we have considered as the angle is same, that's why this is again theta, that's why this is 2 multiplied by theta plus phi is equal to 2 theta, plus mp multiplied by theta plus mp multiplied by theta. So 50 delta plus 25 delta is equal to 6 mp multiplied by theta, and after considering the tan theta is equal to delta, or we can say that the tan this delta is equal to this distance is known to you, we get the value of delta, and this is the value, delta is equal to 4 theta, and here this delta is equal to 1 multiplied by theta. So we get the mp is equal to 25 kilonewton meter. Now we get the three values. First value is 18.92 using the beam mechanism, second 25 kilonewton meter using the sway mechanism, and third using the combined mechanism we get the 25 kilonewton meter. And for the MP we can take the maximum of 1, 2, 3. For the safe load we can take the least value. In case of plastic moment we can take the higher value, and that's why out of these three, MP plastic moment is 25 kilonewton. Now this is the total syllabus of the SA1 unit number 6, plastic analysis, using the static method, that is the lower bound theorem, and the kinematic method, that is the upper bound theorem. Thank you very much.